This is going to be Reifying execution, the interactive programming missing piece, or the simple trick pop programmers don't want you to know. Pop here being place-oriented programmers. And this is the agenda we have for today. So Reifying execution, what I mean by that, and why I think it's an interesting concept. Then we're going to see what this does it enable. If we implement the ideas I'm going to show there, what practical things it enables. I'm going to have some live demos here. And after that, we are going to see a little bit of the how. So some implementation techniques, how this stuff that we're going to see on the demos work inside, in case you're interested in them. Yeah, so let's jump into it. So what first? First, probably most of the people in the Clojure community is already familiar with the Reify term, but for those who don't, Reify means make something abstract more concrete or real. In this context of a Reifying execution, it means make execution tangible and observable. And yeah, this is going to be talking about Reifying executions as data, and not about continuations. So what I mean by this is we are going to be talking about recording execution. We're going to be talking about recording function calls, function returns, value bindings, expression values, and how everything relates to code. And after we recorded this execution and data, we are going to provide ways to interact with the recordings. So a small note before moving on. This talk is about Reifying execution at development time. A lot of these techniques here can be applied in production context, but what I'm after here is improving our development experience, enhancing this interactive programming stuff. But yeah, keep in mind, we're going to be talking about development time. So why first? I think one of the prime value proposition of using like Lisp languages like Clojure is that we should be able to interact with our live program, our live process. And we can already do this with the repls, which is nice, but I think we can go further. So currently, we can fire a function on the REPL. If we want to try some subpart of our system, we can fire a function, run a function that will fire a bunch of other functions, and we can check the return value, or we can see some side effects and stuff like that. But all functions for us are still black boxes. And it's hard to know if the return value is not what you want, then like you just get to look at the code or run subparts of it, or stuff like that. And I think it's much easier to interact with something we can see. And it's not only about debugging. Like most of these like visualization, execution visualization strategies people associate with debugging to try to find a problem or something that doesn't work correctly. But I think it's I see it more as a tool for understanding systems. So we can understand systems by looking at the source code and diagrams and documentations, and that's fine. But I think we can get a lot of insights from looking at concrete executions, so looking at the execution. And I think this is especially interesting in a dynamically typed language like Clojure, for which we have like less information available on the source code. So if you're a Clojure programmer, which you probably are, you're used to this, like when you're looking at the function and you look at the you need to rely a lot on doc strings and the name of the thing, because we don't have types, so we kind of need to guess around the values. So yeah, when trying to understand a code base that you're not familiar with, being able to look at particular executions and the values and how everything relates to code, I think it's we can get a lot from it. But it's also, of course, about debugging. Since for hunting bug, you need to understand the system. And if I can visualize how it's working inside, then, I mean, it's much easier to try to locate where the bugs are hidden. And you can also we can also transform our debugging sessions into data analysis problems. So if we recorded everything that happened while a system ran, then we can try to, for finding the bug, we can use like data analysis techniques for trying to isolate. We're going to see examples of all this stuff. Currently, I think people use some ad hoc system for trying to make the execution more tangible. For example, things like tracing, like print line, logging, and tapping, and all that stuff. It's already a way of trying to, okay, I want to make that execution more tangible. At least I want to try to visualize, is my program like even calling this function? Is it taking the else branch of this if or whatever? And this is great. People do it in every language. But I think it has some cons. For example, like the too few or too much logging. When you add logging or printing or whatever, if you add too many of them, then they generate a lot of noise. If you add too few of them, then you are looking at something and you cannot understand because it's not telling you the part you need to know about. If you are trying to find bugs or understand certain things, it's not easy to know where to add them. Sometimes you just go and guess. Let's add some print statement here and there to then run the thing and hope that it will show me what I need for debugging this thing. And if we are printing or logging to the console, then it's hard to understand complex values. If those values are just numbers or very small maps or vectors, that's okay. But if we have like very big nested maps or whatever, it's going to like, generate a lot of noise on the consoles. And this is there are some tools that people have been working with, like Portal, like combination with Tap and Portal and Morse, or these tools that allows us to, okay, let's no log into the console. Let's log into these different tools so we can inspect nested values and stuff like that. But again, this technique doesn't work if you don't know when to put your tabs, or you really want to use this technique to try to understand, for example, a big system like a compiler. I want to run the compiler with this input, and it's going to generate this thing, and I want to try to understand what is happening inside. And then you cannot add like a lot of tabs or login or whatever. And on the other side, another way of like visualizing the executions are steppers. Most language has like these steppers, which are debuggers that allows you to put a breakpoint and then step over an execution. But I think that there are amazing tools, but they are too fine-grained. If you want to use them to like try to understand how a compiler compiles something, then I mean, single stepping, it's very annoying, and also most stepper works forward only. So when you're trying to wrap your head around something, moving forward only doesn't, at least for me, doesn't really work, because you want to constantly be jumping back and forth, and now you understand a new thing, and you want to go back to see if you like understood something that happened before. But this with forward only steppers, then yeah, every time you want to check something that happened before, you need to like restart your process and step back to the position you want. So okay, so what does this enable? All this stuff is like theory of let's record everything a program is doing, and then let's provide a way of visualizing it or interacting with execution. So here's the demo time. So recording executions enables tools like FlowStorm, for example, which is a tool to try to understand the debug systems in general, Clojure systems, or things like Clofidence when you want to create test coverage reports. So you run your test, and then you want to kind of record everything that is happening, so you get your test coverage reports. Or like DynaSpec, which automatically generates function specification from test executions. This is like the same thing like Clofidence, but instead of trying to generate coverage reports, you want to like run your test and extract, if it's a library, for example, run your test and extract documentation that but not like just doc strings and stuff like that, but also like calling examples from each function, what types have been seen while running the test and stuff like that. So we are going to start with FlowStorm here. So for people that doesn't know, FlowStorm, it's a tool that allows us to record each. So we run our system, we record each thread activity into a timeline, and then we have our execution as data. And then FlowStorm will provide ways to explore and interact with that execution. It will provide visual means, so we provide a graphical user interface where we can explore what happened with our execution, and then repl API, so we can programmatically explore the thing. And we're going to see examples of both of them. So here on the previous slide, I'm talking about like recording each thread activity into a timeline. This slide, we are going to see it a little bit after, but what I mean by this is like when our program runs, we are going to record in a timeline. So this is a data structure, which is just an array, and time flows from left to right. And what we will be doing, we will be recording for each thread things like, okay, this function got called, and then an expression executed, and now another function got called, an expression, and now this function returned, and now these expressions belong to this function, etc. So I want you to have this simple structure in mind, because the entire demo, all the toolings I'm going to be especially in FlowStorm, are going to be over this data structure. So it's pretty simple, the thing under the hood. And yeah, the function call thing here is something like it's a small object where we have like the function name space, a pointer into the source code. So we can see, okay, this function call is related to this source code, and stuff like that. And then expression execution, we have a pointer to the expression value, so what the value was, and also a coordinate, so we can find relate this expression has to do with this specific part of the code in the function or whatever. And same from function returns. Okay, so before running the demo, I wanted to show, to demo, trying to understand a code base that is not like a trivial code base. It's not like just a very simple function. So I think I grabbed it like from the open source stuff we have, the ClojureScript compiler. Why? Because it's kind of complex, and it's also open source there, and everything is written in Clojure. So the ClojureScript compiler, for people that don't know, it's a compiler written in Clojure. Yeah, so a little bit about the architecture. We're going to be running things, so because you are going to see some terminals, and so you don't get lost. It's we're going to be running like just one JVM. Okay, inside that JVM, we're going to run the CLJS REPL, which will in which we can type things like some ClojureScript code, like this function, and the CLJS REPL will execute the Clojure compiler. And it will compile this into JavaScript, and it's going to automatically send this into the browser. But under the same JVM, we are going to be connecting another Clojure REPL. This is our normal way of developing Clojure. So we have a way of interacting with the compiler or whatever. I'm going to show everything in terminals, but this is like the way you normally connect to your process, and from Emacs, Calva, or whatever. And on the same JVM, we're also going to be running FlowStorm. So we are going to be executing this while recording what is happening there, and so we can then take a look at the records. And also, I I didn't put it here, but we are going to be using a dev compiler for that I'm going to explain later. But this is, yeah, I want to show what was this enabled. So back into this. Whoops. Okay. So here we are. We have this thing here. This terminal here is the Clojure script repl. So this thing here. And this is the Clojure repl. And I also have FlowStorm running. This is not like a FlowStorm tutorial, so I'm not showing how to set everything up. But there is all those steps are on the user guide. So I just want to show what this enables. So here on the Clojure script thing, we can do or sum or whatever of A and B, and it will return like this. And it going to evaluate that function that is sending that into this browser here that I didn't show. But this browser here, so if we look at, if we do like this, JS alert 2024 or something, it's connected. That REPL is connected into this browser like here. Okay, so we gave this expression to the Clojure script compiler, and we can take a look with like this sum. We can take a look that it generated this JavaScript, and then it sent it to the browser. So that is what the Clojure script compiler does. But now I want to try to understand, like, for example, how does the Clojure script compiler works inside. I can just go into the sources and try to imagine everything by myself, looking at different namespaces. But I can also try to say, okay, can I record everything? For example, I will just hit record here. Okay, and now we do the exact same thing. Let's evaluate this. Okay, and now everything is being recorded, and we can pause the recording. And yeah, here already we can see that there has been activity in many threads. So just giving this piece of text to the Clojure script compiler, it fired many threads. We are only going to be seeing this one in particular because all of these are related to sending stuff to the browser and stuff like that. But again, here we are already getting some insights because you can explore what these other threads are doing. So let's jump into this. Okay, so I can double click this, and it's going to show me a lot of stuff. I will go coming back to this tool in particular, but the compilation process called a lot of things, and we are going to be interested in this in particular, eval CLJS. So we are going to start from there. So so this is the function eval CLJS, and here we can see the timeline. So this is like the length of the timeline, which is the timeline for this thread, and this is the current position we are. Okay, so we can start hitting next, for example, here, and we are going to be moving, single stepping into this. So we are just moving on the timeline, but we can see, because we recorded everything and we have context on the code and everything, we can, for example, already provide a stepper like this. So that allows us to single step things, and it will automatically jump into other functions or stuff like that. Every time we step, we don't have to step like single step. We can step back and forward, and we can click around, jumping into those positions in time. Every time we click on something, we are going to see the value that was returned by this expression. And yeah, so this is already, I think, much better than working with a simple stepper, because we can move around. And yeah, then we can also inspect values. For example, if we see some value that we're interested in, this is like a pretty print, but it doesn't show everything, but we can inspect it. And now we can dig into more complicated values. This is for people that has used Portal or has also used like Morse and tools like that. It's like that. So allows us to dig into values. But here's where I think we can get a lot of value by having this interactive programming. So if we are looking at a value that we think it's interesting, and we want to like keep working with this value on the REPL or stuff like that, we just like click one button, give it a name, M or whatever, and then we are going to have it here on our REPL, on our Clojure REPL. Okay, so we can go back and forth and bring values into the REPL, and then we can execute stuff from here and record again and stuff like that. So yeah, that is that. But of course, like single stepping, I mean, if we want to take a look at the entire compilation, the thing that transformed this into this thing here, single stepping it's not going to be a good idea, because there are like 100,000 steps on the thing. So for that, we have like other ways of looking at our execution timeline. The second one is like we can look it as a tree. So we can keep expanding. For example, this is the eval CL.js that got some arguments here. So we have these are the arguments of the function, and this is the return. And we can keep expanding things here. For example, here we can see some emit string, which is interesting because it takes some arguments and then it emits, it returns a string with a lot of like JavaScript stuff. And again, we can inspect this, or we can give it a name like emit or JS or whatever, give it a name and come up here and try to do, yeah, there we see the string, or we can do like a print line, JS thing. So it's looks like a bunch of JavaScript that it's somehow contains our JavaScript here in the middle. But yeah, we're going to see what is that about. So yeah, and if we want to like dig deeper into this, now we are like interested in this particular function, for example, emit string, we can double click and just jump into that that position in time, on the timeline. So we can then like step over it and look at the finer detail. Yeah, so, but there are other ways, not only like we can look at our timeline, explore our timeline in different ways. One is stepping, the other one is like looking at the tree and starts expanding things. So this is kind of like a top down view of the execution. But then we also have like this other view. These are all the functions that has been called on our execution. So and we can look at them here, at all of them, but we can use, for example, this search box. So if we are interested, for example, in parsing, we can search parse or whatever. And all of these are functions that has parse on the name. And it's already interesting. These things on Magenta are multi-method calls, and these are like simple functions. And we can already see from here that it's, there is a multi-method call parse, and this is a dispatch value. So it is dispatching on let, on if, and this look like what is, the function that is being called to parse a let or to parse an if statement. This has been called 2 times, so we can double click here, and it's going to show us the arguments and the return value for each of those calls. We can remove some arguments if we think they are annoying there. And here we are seeing the third argument. And yeah, we can see that the third argument to the parse starts with a form of a let. So this is parsing a let. If we look at this, it's probably a form that starts with an if. These are the things that are parsing. And but we can, if we are interested in how this is parsing this specific let statement, we can double click there, and that will take us to here. And now we can like single step and try to figure out the internals of parsing a let, which is going to call like an analyze let if I keep going there. And now we can step into analyze let or whatever. Let's jump into, I don't know, how it parses. Let's try something different. Like we can also see here, like, for example, emission. And if we look at the parses we were looking before, what the parse returns, it's a map. So it basically grabs a form and returns a map saying, okay, this operator is a function and has some things like the names and stuff that it could figure out from here, the oddities and stuff like that. And then we can go, for example, to look at the emission. And here we see another multi-method that's it's emitting stuff based on what the operation is. So there's going to be something for emitting functions, and we can double click there, and let's bring back these arguments because we need them now, and we can jump here. So here we can single step this, and so another interesting thing is that we have here, for examples, it's being able to reconstruct from the timeline all the locals that we have available at this step in particular. So all of these are probably coming from here. And we can also take a look at the stack because we have been jumping around, and we probably want to take a look at the stack, like how did we get here in the first time? And here we can, okay, we are in emit function, that we are coming from this and from an emit def, and all this stuff is coming from the eval CLJS we are originally jumping, but a lot of cascading functions here. This is pretty useful also to try to wrap our head around, for example, on how do we get into emitting a function? And we can see all this stuff. So here, okay. So let me jump now into, if we know the name of the function, for example, we can also type it here. If we don't even know in what thread it was recorded or something, I want to do eval CLJS, for example, and it will take us to the first call of that function. So here we are, and so we have a way of like jumping very fast. We don't need to search in any of this stuff. If we know the name of the function and we want to like show me an execution for this function, and I want to step inside, we can do this. But single stepping is not the only way we can move around the timeline. So for example, here we are calling evaluate form with this form, which is basically the form we provided for compilation. And let's say we are interested in other code that is touching this particular form, like what is the compiler doing with this form I'm giving? And we can use power stepping for that. So this time, every time we click next here, it's going to take us to the next position on the program that is manipulating this value, and it's searching by pointer identity. So yeah, we can keep clicking here, for example. And here, for example, we reach a point where it is wrapping our form. And if we click this, we are going to see here that is wrapping our code with a lot of extra stuff, which is interesting because it's all the stuff we are seeing here. And this is because the ClojureScript compiler is not only compiling the thing that we gave it, it's also wrapping it with some functionality that's going to be useful for the REPL. Before sending it to the browser, it will wrap it, and that is why on the emission we were seeing that stuff. And yeah, so since we are jumping around a lot for trying to understand the code base, we probably want to bookmark certain parts that we find interesting so we can come back later. So here we can, for example, add a bookmark saying, looks like we are wrapping here or whatever. And then, I don't know, keep exploring the thing. And here we can say, okay, interesting, something. And then we have bookmarks here that we can use for jumping around very easily. And this allows us to build, as we explore, we start building a map with a lot of bookmarks or of things we are starting to recognize in this execution, in this code base. Or if we are searching for a bug, then we can make small notes of like, this thing here looks, I don't know, suspicious or something, and then you can go back after. And yeah, there are other things we can do with the timeline also. So let's get rid of that. And let's jump into a particular function for demoing that. So this is the compiler emits function. And this is the function that that writes pieces of JavaScript into a string writer. So this is the function that a lot of things call this thing in order to like generate pieces of JavaScript of the output it is generating. So, but this is being called like, if we look here, like 364 times. So these are the places that you normally want to put, for example, print lines, because you add a print line there, you run the entire thing, and then you see, okay, all these things are being emitted or something like that. And we can even do that on top of the timeline. So we can, for example, right-click here and add to prints. Let's give it a name like out. This is like the message you normally put on your print. And then we have the printer tool here, where it's listing all the prints we have. It's only one print so far. And we can say, okay, run all those prints on the main thread. And now we have all the messages here. So with this, we can, of course, we can add more prints in every other part of the code, and then they will be in order and everything here. And this is also searchable. So are we emitting everything that has to do with SAM? Looks like we are. But when we use print lines on the console, then you don't get a way of saying, okay, I'm interested in this thing. What is emitting this thing? What we can do is we can double click this and jump into that point in time on the timeline, and we are back into the precise time where we are emitting this particular value. But now we have the stack. So we can move around and saying, okay, it's emitting that thing. We're coming from a def emission. And then I can like double click there and jump exactly to that point in time. And now we are, trying to figuring out how like def works, or def emission works, or whatever. Yeah. So FlowStorm have many other tools. I don't have time to cover all of them, and this is just like a demo so you can get an idea of what like this execution like Reifying executions enable. So let's get rid of this, and okay, let's go back to the slides. Okay, I have just show you how you can interact with the visual interface, how you can interact with the timeline we just recorded. But there are other ways of interacting with it, for example, programmatically. This is the thing I was telling before, like, because we can program against this recorded data, then we can transform our bug hunting into a data analysis problem. So yeah, let's take a look at the bug first. So this is a real bug of I ended up submitting a patch that ended up being a problem with the tool readers, and I used FlowStorm to debug it. Not this technique, but this technique could also be applied. So what is the bug about? So when we evaluate something on the CLJ, on the ClojureScript REPL, we can evaluate a function. And if we add a meta here, a map saying line 42, and then we go and check, okay, give me the var, give me the meta, and give me the line, it says 1 instead of 42. So, and this is something that works in Clojure, and it doesn't work in ClojureScript. And it's important for tooling. So how can we debug this? So there's look like this line I'm putting there is getting, I don't know, lost somewhere or overwritten by a 1 or whatever. And we can, of course, record the execution and fire the UI and try to explore and follow values and stuff like that, which is one way. But the other way is to transform it into a data analysis problem. Before looking at this code, let's look at this. So one approach we can have for this is we record the compilation of this, and then we have a timeline. And what we can do is like, okay, let's walk the timeline, and let's try to find position where we an expression evaluates to a map with line 42, and then from there we keep walking until we find a map with line 1, and then we, for example, collect these situations. And if we collect these situations, we have like places like, okay, we have this map that evaluated to line 42, and a little bit after it evaluated to line 1. So probably we want to look at that part to see if the bugs it's hiding there. How we do that? It's FlowStorm exposes some API that you can use, so you can get the timeline, and it's called the timeline index, and you can like loop around and do some simple logic here. If we are, I don't want to go into details of this because it's just like one implementation of this search here. But you can imagine that you can search. But we are going to see a demo of this. So let's try a demo of this. I will use a cheat sheet here, so we don't need to type all that stuff. But first, let's try to reproduce the bug. Let me clean this here. Okay, so we do that. Slow because I'm kind of streaming. And then that. And that should say 42 and now says 1. So yeah, there is the bug there. So let's try to record that. For that, sorry, we hit the record button here, and we do this again. So we get a recording. There we have it. And now we have the recording, but we are not going to use this. We are going to use the REPL, the Clojure REPL, to explore that. So I'll copy stuff from here. This is just like requiring the API stuff. And now we are going to get the timeline. So timeline index is now a timeline we can use. And now I'm just going to copy and paste this exact same piece of code to try to find the positions there. Okay, so we say that we typed all this stuff on a REPL, and it's finding a couple of positions. And I already went over a couple of these, which are interesting, but the bug is hidden here. I don't want to take you over all that stuff. But as you can see, we can, since we have the timeline position, we can open this. Doesn't matter. We jump. Doesn't matter because we are going to type that number here. Okay, and we are the debugger takes us exactly into like something that's evaluating into a map that contains line 42, and just a little bit after it has line 1. So doing some kind of like data analysis or whatever, or a search, we were able to quickly find that, yeah, this map is being overwritten with something that contains line 1, which shouldn't be the case. This is already like fixed. I changed it one line here and submitted the patch to tools reader and it's already merging. So yeah, this is another way we can debug our programs, or try to figure out some interesting things from our execution. Okay, so I think I have one more demo on this. So yeah, so far we have seen one timeline per thread. But there is also possible, it's not doing that by default, but it's also possible if you are trying to debug multi-threaded programs, you probably want to like record all your thread activity into one timeline, so you can take a look at the interleaving of different instructions if you're trying to understand race conditions or stuff like that. So yeah, for that, we are going to use not the ClojureScript compiler, because I didn't find there like a nice thing, but something much easier. So I'll just start a namespace here, doesn't matter, and we are going to define the factorial function. This is so we have something to compute. That's nothing important about this, but we are going to do a parallel map. So we do some multi-threading stuff. Okay, we do some parallel map there, and all these factorials are running in parallel over this range. But let's bring back the debugger. Let's enable the recording of the big timeline, so the one that includes every thread, and let's enable recording, and let's run the parallel map again. And now here we see again like a lot of things running on different threads. So this parallel map, it's running on one thread, but then it's fighting like the factorials. If you look at different threads, these threads from the pool that the parallel map is using, it's running the factorials for 3 and 6, and there are other threads running like factorial of 2 or whatever. But if we come here into the timeline, we can now bring the timeline, and now we are going to see how all the threads instructions interleave. The same thread has the same color, so it starts by evaluating the range of 7, and then it starts calling things in the parallel map, and yeah, we can see this color is not. It doesn't work with this theme, but anyway, and we can search stuff here. If we're interested, like, I don't know, I can put like lazy or something like Boolean or something, and I can see like everything that returned Boolean types or stuff like that. But we can also, if we are interested in this particular instruction, like here, we can double click there and jump exactly into the that point in time, and yeah, we can debug from there. I was a little bit on this 0. Oh, that's interesting. I think I found a bug there, but interesting. Okay, so but again, this is a way we can see how everything interleaves. And I haven't used it a lot, but it's there, and yeah, and I think that is all for the FlowStorm demo. We can get rid of that. Okay. So I'm not going to these other tools. I'm not going to go deep into them. Just like an overview of what is the thing enables. So Clofidence, it's the thing of we instrument everything and create test coverage reports. It looked like this. For example, I have created one for the tools build project. So this is just we run the tools build project and collect run the tests and collect everything it's doing, and then we can see things like, okay, these are all the namespaces and the coverage they have, And then for each namespace, we get to see every place that the tests are hitting. For example, the green stuff is places that the tests are hitting, and the red stuff, it's places that the tests aren't hitting. So we have like a nice way of looking at our things. And for example, the tests are never throwing this exception here, stuff like that. But that is another thing that is enabled by this Reifying execution thing. And then there is this DynaSpec that this is experimental and unreleased yet, but it's let's automatically generate function specifications from test executions. I have I think a demo here because I ran. Let me start FlowStorm here. FlowStorm repl. This is I already ran and generated all the specifications for tool build. So same thing. I ran tool build tests with everything instrumented and collected all the specifications. Let me increase the font a little bit. And now what I'm doing is I have FlowStorm has capabilities for displaying this kind of documentation in the docs thing. And you can load documentation from many libraries. But here we can see, for example, all the functions that were executed by the tests. We were able to collect the specifications. So now we can see things like the arguments that are known for us. And for example, this POM, it's a node element. We can see the type. And we can see the path is a persistent vectors of the strings, and we can see that it's known to return an element here, and we can see examples of how this has been called. And yeah, all this is tool build, so we can go to install, or here, install, and take a look at the documentation of install, and stuff like that. But there's a ton of work to be done on this side, but I think it's an interesting idea to explore on top of the same thing. Okay, and that was it for the demos. So let's go to some slides again. So has this been tried already? I think it's an honest question. I did to myself, asked this to myself, and then after like a couple of years working on FlowStorm, and I did a bunch of research, and it kind of, but I didn't found. I read papers that started in the early 2000s. I even had a meeting with Bill Lewis, the guy that I think that coined the omniscient debugger term thing. He was like trying to give talks at Google Tech Talks back in the early 2000s. And we discussed about this stuff. And there are tools currently trying to do this thing, but to be honest, I have tried them. I recently tried something for Java and for C++ also, and they are kind of the same, but they are not the same. And I think it's because of mutability. Most of the languages I have seen this kind of tooling are languages that work with mutable data structures, and that makes recording and replaying things much slower, since you need to record side effects and then try to inflate the objects from your recordings. And it also has less features. And I think it isn't on other languages, it isn't that useful without interactive programming. I think it's much useful, this kind of techniques for us, because we can like go and run and record subparts of the things we are interested in. And it's not like, let's record everything the process is doing from scratch or stuff like that. And yeah, so now for the final part of the presentation, let's look a little bit on the how all this recording is implemented. So how? With this simple trick, pop programmers don't want you to know. And it is that immutability makes recording values cheap, very cheap, because recording all values when a system is running, it's just leaking pointers, so the garbage collector don't grab them. And yeah, what about mutable values? Since Clojure can work with mutable values, we still have an escape catch via value snapshots. For this specific case, think like data file. So we can take a snapshot if we are interested in specific values. We want to record snapshots. We can do that kind of stuff. So how does tracing work in general? So the tracing, we saw this timeline that we are recording stuff there, but we need to be able to trace them. So when the system runs, something should happen. So like each step gets traced. And it works by interleaving instruction to trace. So we grab our piece of code and we instrument it, which means that we interleave instructions. So when the final thing runs, it's going to trace function calls, function returns, expression values, and bindings. How can we do tracing in Clojure? I have been working with two techniques, the old technique that FlowStorm used to use, and a new technique. So there are two options to interleave instruction for some piece of code or an entire code base. One is at macro expansion. So you surround your piece of code with a macro, and when that macro expand, you macro expand into something that has like interleaved instructions. This is implemented in the Hansel library. This is not what we have been running on the demo. We have been running on the demo this stuff here that yeah, we'll talk about next. And so the other ways we interleave instructions at the compiler. This is like, what if the compiler itself, when it's emitting its code, JVM bytecode, it interleaves in instructions already, extra bytecode there. And this is what these two projects are about. ClojureStorm, we are going to see it more in detail. It's a dev compiler that is going to do exactly this for us. And ClojureScript is the same, but for ClojureScript is the same for ClojureScript. So let's look at the ClojureStorm compiler. So ClojureStorm, it's a dev compiler, so you swap it for development. We can, luckily, we can do this easily in Clojure because the Clojure compiler is just a dependency. So we can swap it and use another compiler. And it's a compiler that's specifically designed for development. So it's not about performance and all that stuff. You are supposed to swap it for your development, and then you run your test with your normal compiler, and in production, of course, with your normal compiler. It's not a compiler that I wrote from scratch or anything like that. It's a fork and track the official Clojure compiler. So it's the Clojure compiler with some patches on top of it that will emit extra bytecode that will trace code by calling some predefined callbacks. It also has knobs for enabling, disabling instrumentation, control what gets instrumented, and a couple of other things. This ClojureStorm project has nothing to do with, I mean, it's not coupled in any way into FlowStorm. So you can use it for your own projects. Now let's look a little bit inside of how ClojureStorm works. We are going to look at a small disassembly. This is JVM bytecode. But if you have never seen it, don't worry, I will explain a little bit about it. So what does the Clojure compiler does when you ask it to compile this sum? So we give it to the Clojure compiler, and it's just adding the two numbers. So what the Clojure compiler does, it emits bytecode of only the things that you see in black here. Forget about the green stuff first. So when you compile this, it will create a class called user_sum because it's inside the user namespace. And this class will have like a couple of things, but most importantly, one method that's called invoke static. And that this method will be fired when you call this function. What is it going to do? It's going to put a reference to for this expression, it will put a reference of the first parameter into the stack. It will load A into the stack. It will put a reference of the second parameter, so B, into the stack. and then we'll call numbers add that will grab both value from the stack, add them, and leave the result on the stack, and then it will return. So this is how like Clojure works under the hood and at the bytecode level. So the green part is the stuff that the extra bytecode that the ClojureStorm compiler emits for us. And yeah, so in the beginning, it will add a call to trace the function call. So when this function is called, it will call trace function call. And then, for example, it will, when the system loads the A parameter into the stack, it will duplicate it and then basically call trace expression with another copy of that reference, because this will consume the copy from the stack, and a coordinate. We are going to see this in a couple of slides. And so it is doing that for this. So it's basically calling trace expression with this, then calling trace expression with a duplicate of B. And then after the numbers add is called, so after this is called, this will leave the added number on the stack, a reference to that number on the stack, and we duplicate that and we call the return, trace return with the final value, and then we return from the function. So it's pretty straightforward. It will just add some extra thing to trace different parts. And again, this is the same slide we were seeing before, and I added it here so you can see how this matches with this. So every time this does a trace function call, it will end up here. We will add that function call into the vector. Every time it does a trace expression, it will end up here. So things will be firing, and we will be collecting them on a timeline. So it's pretty straightforward there. And now there is one other thing. So we are recording the values, but we also need to record how these values refer to our source code. And we do that with two things. So functions are going to have a form ID. This is just a map of all that goes from, we are going to see it now on the next slide. And then for each expression execution, we also are going to have a coordinate, which is where inside the form that expression execution refers to. And the same for the return value. Okay, so a little bit about this form registry, how we match things to the source code. So the functions will have this form ID, which is like a reified pointer. And the registry, it's a map from form ID into the form source code. And yeah, and the form ID, it's a hash. It's calculated with a hash of the function form. And yeah, this is what I was saying before. All function call recording have a pointer to the form ID, and all expression execution have a pointer to the function call and also a coordinate. How does this coordinate work? So we need to be able to talk about like specific, if you saw on FlowStorm, we are painting different things with different colors. So you can see, okay, this value is coming from here. There is a coordinate system here. That is pretty straightforward. It is like get in coordinates. So for example, for this form, this will be coordinate 0, coordinate 1. This vector will be coordinate 2. And here, for example, this plus is going to be coordinate 3, 0, and 3, 1, and so on and so forth. There is a little bit more on coordinates for maps and sets, because the order is not persistent there, but don't worry, this is a special case. We are not going to go deep into it, but there is what I wanted to show here is that there is a solution for every possible piece of source code. But for the most, coordinates are these kind of things. And if you look into disassembly, this is why we are, when tracing the A here, it is saying, okay, this is the reference, the thing that we duplicated from the stack, and the coordinate is 3, 1. And this is 0, 1, 2, 3, 0, 1. So this is 3, 1. Yeah, and that's how the coordinate system works. Now, by the way, this coordinate system, I got this in the beginning from like kind of copied from the Cider debugger source code. So thanks them for the idea. And yeah, and then how there is an extra thing like dealing with macros. Like the user writes a source code that is macro expanded, and the compiler is going to compile the macro expander code. So how we can like join everything together. And this is because what we currently do is we tag before macro expansion inside the compiler, we tag the forms adding meta to all subparts with their coordinates. And then we macro expand, and then we only instrument code that has a coordinate on the meta. So we are not adding extra bytecodes for things that are coming from the macro expansion that has nothing to do with what the user is seeing on their code, because it doesn't make any sense. There is a little bit caveat here. It is that if the macro when it's generating its output code, it's not preserving the meta of the form that it got as input, then this can break. But in practice, doesn't happen a lot. The one thing I know it kind of happened, it loses some meta, is on the Clojure corasing Go block macro. It's a very complicated macro. And I think also I have seen it on some Clara rules macros and stuff like that. But in practice, it isn't a problem. And yeah, before closing here, a little bit about FlowStorm performance note. So first, instrumentation can be controlled to balance detail and performance. There are some ways like skipping unnecessary namespace or things that are not interesting to you, or limiting the recording of noisy functions. If you have like a function that is being called like trillion times and it's not even interesting for you, you can like disable, don't instrument that function or stuff, or record just like 5 samples of that function and then stop recording that specific function or stuff like that. Now, the performance of the instrumented code depends quite a lot on the code itself. But for example, on this thing of instrumented, I have measured this ClojureScript compiler instrumentation. And if you say like the official ClojureScript compiler runs in 1x, then if you have it instrumented but you are not recording anything, then it runs into about 1.8x. This is so because we are not recording most of the time, so it's going to be a little bit slower, but doesn't in practice it's not much. And while you are recording, then yes, it's going to like 10x, which is an order of magnitude, but that's only happen when you are like recording something, and you are probably going to spend much more time analyzing the recordings than at the time that this take to execute. So from experience of REPL-driven development, it feels completely okay under ClojureStorm pause it if you're not recording anything. It's most of the cases unnoticeable. So yeah. So wrapping up, I think recording execution can enhance interactive programming a lot. And Clojure is especially suited for this kind of tooling because of immutability plus REPL-driven development. And I think it's because of immutability, it's even more what we can do in Clojure that what Common Lisp or Smalltalk can do on this side, specifically because of immutability. And yeah, and recording, replaying on demand can be done efficiently. Again, because of immutability, we can just leak pointers and everything executes fast. And the implementation is pretty simple. So if you look inside it's emitting extra bytecode to trade things, and then we build a timeline. And the entire thing, UI thing you saw, comes from like walking the timeline in different ways and showing it in the UI in different ways. And from experience also, like we can get a ton of insights from a recorded timeline. As you saw, we can use it to explore an execution, for example, for the ClojureScript compiler, but you can do this for your web apps or whatever you're running and get some insights of how things are being called, what kind of values, inspect, and everything. And yeah, thanks a lot. And try out all these tools. They are under the FlowStorm organization. And also go ahead and contribute, provide feedback, create GitHub issues, GitHub discussions, whatever. We have a Slack channel. It's called FlowStorm. People go there to like give feedback and I don't know, give some in any way like bad feedback or like new ideas that people want to try, stuff like that. So feel free. And yeah, that's it. So